It's supposed to pull
up. Don't worry, we'll be fine with that. That's fine. Okay, so welcome everyone. Thanks for coming. I mean, I know all of you except maybe one or two. So my name is Sasha Rubin. This is Guillermo Badia. We are delighted to host Professor Geoff Sutcliffe from the University of Miami to give us a tutorial on automated theorem proving. In fact, we have a whole day scheduled, but it really depends on audience interest and participation and so on. I think the first hour is going to be for a general CS audience, and feel free to stay longer if you like. Geoff is also available for meetings tomorrow. So Geoff runs something called TPTP World. TPTP stands for Thousands of Problems for Theorem Provers, but it's actually not just about problems, it's also about solutions, it's about solvers, industrial applications. I'm sure we're going to hear a lot more. Geoff is on something called the TPTP World Tour. Now, if it sounds like this is the schedule, if it sounds like this is a tour of a rock star band, you wouldn't be wrong. So I couldn't find Taylor Swift's tour dates, but I did find the Rolling Stones tour dates when they were touring. Recently, they're not touring as rigorously as Geoff. So when they were touring in the 90s, this was comparable to Geoff's tour. So he's already been in South America. This is his first stop in Australia. And after this, he'll be going to Asia, Europe, and the US. With that, over to you, Geoff.
Thanks, Guillermo. Yeah, you're right. So it depends on the parentheses. The TPTP World Tour, or is it the TPTP World Tour? I thought I should have T-shirts and CDs and autograph signing and all that. So I cut back. It's a correct. I'm from Miami, and I've just been in South America, Colombia, and Brazil, and Chile, giving this talk, doing research with people, trying to promote it. But yes, I live in Miami. But so the long story going back is that I came to Australia in 1986 to Perth, and I did my PhD in Western Australia. And then when I finished that, I moved up to James Cook University in Townsville, where it's hotter and wetter and more cyclones. And I continued. This project had its foundations when I was doing my PhD. So that's sort of early 1990s, and it's still going. So I've had this project longer than most of you have been alive. This is my baby. I don't have real children, but I have this, which is as much trouble as I need. And I'll talk more about the foundations of this. I'm going on. So if you ever want to find anything of mine, it's all online. My slides are online. It's just web pages. So all you have to do is go into your browser of your laptop and go into the settings up at the top right, and change your homepage to tptp.org. So then when you turn on your browser, you'll always be online. And this is one of my talks, Infrastructure for Automated Reasoning. So I guess the backgrounds here are math, computer science-ish of some level. I don't know at what level. So I'm going to kind of assume you just know Boolean algebra, and then which is safe. And if I go too slowly, it's like, come on, speed it up.
I think you can assume an advanced undergrad level up.
Okay, right. So people know about logic, first order logic at least, and maybe some set theory and types and things. Oh, good. All right, genius. All right. And as I said to Sasha, I can do anything from 30 minutes to 4 hours, massive material. So what's this all about? So automated theorem proving is hard, as that picture shows. But what is it all about, this automated reasoning? And so I'd like to kind of show it in terms of this picture here. This is all the words, but just follow the pretty pen. Is the world has problems, and we were just discussing Donald Trump. All right, and we'd like to have a solution, but it turns out you're not allowed to shoot people. Quick solution. So what happens if you've got a world problem and you want to solve it and you don't have a direct algorithm, a direct computational or other style of solution? The game we play here is to take the world problem and convert it to a logic problem with appropriately expressive logic. Take that logic problem and give it to one of these super duper reasoning systems, which there are many types, of course. From that, we get some kind of solution in logic and then reverse engineer it back up to a world solution. That's the game we're playing. And this is good because you can express almost anything in logic. And once you've got a solution, for example, a proof is a typical type of solution, then, or a model, a counter model, reverse engineering it. The game is, this is kind of difficult. And that's if you want to make $1 million. That's like doing software design. Programming is something you can outsource, but doing the design is difficult. And similarly, this part over here, taking a logic solution and reverse engineering it into a world solution is really under research. I mean, there are PhDs sitting out there for anybody who wants to work on that kind of thing. So we're going to look at sort of two types of tools. And just as I'm marking them down here, we look at theorem proving. We take some description of a world and try and prove some property, just like mathematical theorem proving. And on the flip side of the coin, we look at model finders, which is a different type of reasoning tool that takes a set of statements and checks them for consistency. And if they are, produce some data structure, a model that represents that consistency, and we can use that in applications. So we see it like this. We take the world that we want to talk about. Let's say it's biology or something. We describe it in some axioms. Then some problem we want to solve, describe it as a conjecture, hand it to one of these magical tools, and we get back either a proof and some structure that we can understand, or a model that tells you why it's not a theorem. And from that example, that data structure, that model, you can tell why it's not a theorem, which might mean that it really isn't, or that there's some weakness in your axiomatization. And finally, we produce a solution. Standard technology, hot technology now, and people I'm sure have heard of Tableau systems, but they really are not the most powerful systems. The current game is we take the axioms, what we want to prove semantically, give it to a theorem prover, and we get yes, and we're all happy, and we get a proof, we're even happier. Or it says no, that's definitely not a theorem, and we get this counter model, the data structure that tells you why not. Or because this is often just shit hard, it times out after a few minutes. The standard technique is proof by refutation, as you do mathematically. Take the axioms and the negation of the conjecture and look for unsatisfiability. If there's a contradiction in that, yes, no, or timeout. Of course, the sad news with this sort of technique is that if there's a contradiction in your axioms, you still get a refutation. And so this is how you get free beer. The logical way is you go into a bar and you argue with your friends until they contradict themselves. And when they contradict themselves, you can prove that they owe you beer. It's logically sound. No, so who said there isn't a real reason for doing this stuff?
Do you still have friends?
No, I'm drunk a lot. All right, so what are the things you need to do first if you want to do, so this is an engineering game, take your axioms and check your axioms are consistent using a tool, one of these lower type of tools, these model finding tools. It'll tell you yes, and here's a model, why they are. If you know your axioms are contradictory, go back and look why, or time out again, because this is even harder than proving theorems. All right, so what can we do with these things? Well, here's a puzzle for you. Come on, internet. All right. So if you know the answer to this puzzle, don't shout out. But you all graduate students, or at least computer science students or mathematics, so you're intelligent. Here's the three people who live in this mansion: Agatha, Charles, and the butler. Sorry, Agatha, the butler, and Charles live there. And somebody killed Aunt Agatha. And here's the rules. A killer always hates their victim. A killer is never richer than their victim. Charles hates no one that Agatha hates. Blah, 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 blah. I'll let you read that. I'll give you 1 minute. You decide who did the killing. Who killed Aunt Agatha? And if you know, silence. In that text 15. That's easy. I mean, this is trivial in logic.
So are we assuming that if we can work out if anyone hated Aunt Agatha, then they would possibly.
You wish
want
you
to
can
kill
see your
him.
brains now working through it, yeah?
And if there's more than one person that.
No, there's only one possible killer.
But, okay.
Yeah, you can prove that only one person did it, and you can prove that that person did it and the others did not do it. Yeah, okay, yeah, sure. All right, so who said the butler killed Agatha? Who's for the fat butler? No. Who's for Charles? Oh, Charles is going to electric chair. All right. Well, actually, it turns out that it's a suicide. All right, so Agatha killed Agatha. Yeah. And this is a simple thing, but of course, this matters because this is the sort of game you can give to an LLM. All right. And I give this thing to an LLM on a regular basis. I'm going to quickly whip up a window. I can cut and paste the problem into. We'll try because you get a different answer every day when you do this. I never know who's going to send to the electric chair. Is it 10/Aunt Agatha? Okay. Where's the text? Here it is. Just so I can cut it in. All right, blah, 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 blah. Who killed Aunt Agatha? Right, and what's your ChatGPT, Claude, Gemini? Any preferences? Right, let's go with Gemini. That's what Google says today. Oh, well, I did it. I just asked it recently. And what did Gemini say? Oh, the butler. Gemini says the butler did it. But we could ask ChatGPT, all right, and I pay for $20 a month, so I've got the good version. All right. And look what it says, logically analyze. And it's doing what you were doing, right? You were thinking, yeah, well, who's richer? That's what it is. Who hates? Who's richer? Started doing it. And the butler cannot be the killer. Can Agatha be the killer? Yeah, so I got it correct this time. And I think the problem is I've asked it too often while I'm logged in and it knows you aren't. All right, so this is actually one of the hot applications of this technology of mine at the moment is taking results from LLMs, translating them into logic, and then checking them logically, because otherwise, in Texas, Charles only got 2 weeks for an appeal, and otherwise, and you guys have just sent him off, and they're pretty aggressive about it. And you've all heard of alpha proofs, the result that came out recently, where the system that's a combination of LLM and Lean 4 reasoning tool got a silver medal in the National Math Olympiad. And this is hot. There's papers on archive coming out faster than I can read. Okay, so stop raving about that stuff. So now we know the game. How do you make $1 million using this technology? Well, the origins of this are largely from Argonne Labs near Chicago in the US. And they were doing mathematics, particularly a lot of stuff in algebras and related things that are small numbers of axioms and easy to express. The big success story was that is every Robbins algebra a Boolean algebra, which was a problem posed by Tarski in the 1920s. And he couldn't prove it, and his PhD students couldn't prove it, and they gave up. Then Huntington came along and talked about more maths. And eventually this was proved by automated theorem prover. So this is hard math done by which real mathematicians, and Tarski's no fool, couldn't do it. All right. There's a lot of other stuff. This is current work going on now again in algebra with a bunch of real mathematicians. So it's a tool. But there's no money in mathematics. You all know that. So if you're studying maths, prepare for saying, would you like prize with that? All right, so the verification is the hot business. Looking at software and hardware and verifying properties of the software and hardware. Everybody's at it. Microsoft, all the big players at Microsoft and Amazon and IBM and ARM and all that, if you want to do firm verification. I admit they use a companion set of tools, the SMT solvers, if people are aware of them, because they're better at doing mathematics than my tools, and a lot of those things are mathematical, but my tools are also part of that toolbox of doing verification. And if you're into, for example, Amanda is a very successful company that does it. They just got a contract to verify the trading rules of the London Stock Exchange. So I promise you, those guys are buying a big boat soon because they're making money out of it. Reasoning about processes. All right, so you got a thing that cuts metal, you want to make sure nobody's hand is in when the blade comes down. There's all these sorts of rules, we do that. The Amazon people love doing it. Take your database schema and make sure it makes sense. Make sure your network schema is good. Then you start trying to do real hard things, trying to reason about the whole world, is what LLMs are kind of good at because they absorb the whole world and then make up some stuff about it, but reasonably accurately, but not 100%. So how can you do that? And this is business going on right now.
One question, but with your tools, because as I understand it, with a SMT solver, once something is not satisfiable, it gives you almost no insight as to why that is so. But in your tool, you do get some insight. If you do like, okay.
Yeah, right. So it's true with the SMT solvers, some of them produce proofs in the LFE format. And I've just been talking to them, people in Belo Horizonte about it. And when they have a model, the data structure that says why something is consistent or not a theorem, some of the tools can produce some things. Whereas in my tools, that's kind of a big focus. It's producing output that's usable by the people who are posing the questions. And I keep pushing down that track quite hard. So it is one of the different, I mean, we don't have to fight each other because our target games are different. All right, and then there's the real world. And so I've been working with people in Luxembourg, encoding the United Nations Declaration of Human Rights. What does it mean to be a war criminal and things like that? Not be a war criminal, it's easier to tell than if you are one. This beautiful project from Germany took speeches by politicians and encoded them and showed that they were often contradicting themselves. And I love it just because of the acronym, the CRAP project. Voting, this is stuff out of Denmark, going to elections, making sure election procedures are fair, no more stop the steal and all that kind of stuff. GDPR in Europe, of course, privacy, making sure your company is obeying privacy rules. And this beautiful work by Chris Menswell on the existence of God, proving the existence of God. Of course, the ontological argument's been tackled by many people. You have to accept the axioms, then you've got a second order modal logic proof. And this is cool because it got picked up by the German newspaper Der Spiegel when this was done a few years back. And blah, 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 blah. But the key word was this, it was done by a MacBook. It doesn't matter about the mathematics and the logic and the programming. No, you use a MacBook, you can prove God into it. Fantastic work. I mean, it's very interesting work. Right back to the early days from Gödel, going through Dennis Scott, who found mistakes in Gödel's work, and he typed it with an old typewriter. And then that got translated by Benchmuller and Bruno Wolfson-Pollenloger into, then they found a mistake in the typewritten stuff and fixed the proof of the existence of God. All right, boom, boom, boom. And I've already mentioned this stuff, the alpha proof work and things that are going on, combining sub-symbolic systems with symbolic systems. I'll talk about it. I don't want to talk about all the different theorem provers available. There are a lot of them out there. And I've got most of them installed on my server in Miami. And for those of you who are staying on to do a little practical work, we'll be just running them off my server. You don't have to install anything. And I think this is the main picture you should take away from this slide. I've listed a whole lot of systems here. But the main picture is that they're really complicated bits of software, high-performance automated reasoning tools. You better know your computer science for this. You better know data structures, algorithm complexity, advanced algorithms, and all that. Because if you don't, you won't be able to write a tool that's high performance. Really is proper computer science going on. The big winners at the moment are the E system out of Germany, Vampire out of England, and now Austria. Anybody use Wolfram Mathematica, maybe in some of your work? Well, inside that is a famous theorem prover from the Max Planck Institute called Voltmeister. And the guy who wrote that, Thomas Hillenbrand, every time they sell a copy of Mathematica, all he hears is ching, ching, like that. So he just sits in his home and makes glue vine or something. All right, so what's this whole TPTP world about? So this started back, I was writing theorem provers, and I noticed two flaws. I was reading the Journal of Automated Reasoning, and people would write their washing machine, and they'd choose 10 test problems very carefully. Say, look, I solved all 10 quickly. My software is fantastic. And of course, that's cheating. On the other hand, we saw something even worse. We saw, this is myself and Chris Suttner in Munich. We saw people having good ideas, theoretical, and doing a decent implementation, but choosing the wrong 10 test problems and getting discouraged and giving up their research. and we saw that as a weakness. So we said, right, we're going to build a collection of test problems for these automated theorem provers. And as Sasha said, it was going to be thousands of problems for theorem provers, and we have this centralized collection. Since then, it's grown like an octopus. I always have an octopus with me just in case of an emergency. But with lots of features, and I'll talk through some of them today. But I have to show you this review I got once for a journal paper we wrote. I just like this. This is intellectually frozen in a time warp we were, apparently. It's a waste of time. It's counterproductive because I'm luring the young researcher into a style of work that is essentially wasted. The organizers, that was me and Christian, should be forced to drink the poison cup of Socrates. That's a review. No, that's a good review. The paper got accepted eventually, but I've always wanted to find this guy and thank him for giving me such a nice review. All right, so now, get to the right size here, go back. So let's just look at some of the arms of this octopus, and some of them are exciting and some of them are just hard work, but just so you know what's available, part of my mission here is to convince people to use all of this stuff or know it's available. So you do solving some problem in whatever computer science, math or biology or business or whatever you like. Because remember, we can write anything in logic. We're a solution waiting for a problem to happen. So just note about, so here's where we started off with the problem library that we started collecting when I was in West Australia. Look for the joke 1, 2, 3, 4, gone. Okay, now look, TPTP, right? So the first release of this collection of problems, this simple, unambiguous source, a central problem collection, which so we can get repeatable testing. First release was in 1993. And now we're on version 9, and you can see we're up to almost 26,000 test problems. And if you look at the domains of those test problems, you can see we cover stuff in logic, stuff in mathematics, lots of set theory, algebra, number theory and stuff, into computer science, you know, the halting problem, natural language planning, common sense reasoning, semantic web, data structures, reasoning, you know, can you index off the end of an array and stuff like that. And verification of software, as you can see, it's lots of that. Biology, hardware, medicine, processes, a great one on how to make wine. What's the process of making wine and products? Social sciences, so we do auctions and elections. Management of business, how do you grow a business constructively and prove that you have, what are the properties you need? Geography, is Jerusalem in Israel? Philosophy, and of course the fun stuff, puzzles like the Aunt Agatha problem. So it's very broad. We go, at the moment, we have 6 logics. There's a lot I could talk about here. Propositional logic, first order logic, typed first order, so first order type what you want. Extended first order, which allows you Boolean terms, so you can do he said that, she said that, I said that, you said as a liar, these sorts of arguments that if you want to analyze political speeches and stuff, you need higher order logic, and we've just moved into non-classical logic, so now we support modal, deontic, epistemic logics as well. So we have tools and languages for all of this. The problems are written in this fantastic language. I think so. All right, so here's that Aunt Agatha problem. Anything that begins with a percent is a comment because it comes from the prologue heritage. Now we've got the English story of what it's all about, references, so you can go and find out, oh, this paper over here, on internet, there it is. These papers have referred to that particular problem. And then we know what it is. It's a theorem. This can be proved that this one is that Agatha proved killed herself. That's what you wanted to ask about. If you try and prove that the butler did it, no, but then you can prove that the butler did not do it. All right, and one of the cool things is we have this rating system, and 1 means no theorem prover, no software I have, and I have all of it, can do it. And 0 means everyone can do it. And 0 means if your prover can't do it, you should transfer into sociology. Bunch of syntax about problem specifications. And also we classify the problems into like different types of problems so they're somewhat homogeneous. So this is a first order theorem. It's really first order. It can't be reduced to propositional. It's got some equality. Here's the language. So here's the first thing. Every first order. Every formula has a name, so you can write out proofs in models. Its role is this is an axiom. There exists X, question mark is exists, not the backwards E, by the way. That such that X lives in the mansion and X killed Agatha, full stop. All of the symbols that you use when you're typing this are on your keyboard, which always reminds me of the computer science joke. Why do Emacs, everybody use Emacs editing? Why do Emacs users have flat noses? The answer is because they used to go Control-Alt-Shift-Letter-P. All of my stuff, you don't need any of that. Everything's just plain old ASCII. All right, and here's the conjecture. So this is the conjecture that Agatha killed Agatha. The language is very simple. It's designed to be human readable and machine readable. The grammar is LR1 for anybody who's into compilers and stuff like that. I could talk about the language, but then I get too excited. If I have to just show you why I don't like SMT. So here's a simple thing in mind. There exists X such that P of X, 1 implies equal X1. Well, if you want to use a little more disk space, you write it out in SMT lib, or you just write it out in XML and then buy another disk. So the language is, you see, this is more designed for machine level work, which is what SMT is good at, better than what my stuff is. This is designed to be readable by people as well as by machines. That's the language structure. And because it's LR1, you can just throw Lex, Yak, or I've got Antilogramma export, so you can just build yourself a parser in anything you want in this language. All right, and it's all available. You just go to your home page. All right, and there you go. So after we did that, and we published a few versions of that, and then we thought, what should we do next? And I'd moved up to James Cook University in Townsville, and I started building the TSTP, thousands of solutions from theorem provers. And one of the things I realized when I was doing this is you need to say quite precisely what you mean. If you run an SMT solver, and I love beating these people, you say check sat, right? And it says sat, which is unsat. Well, quite often, because it's complication, the best answer it often gives is segfault. That's not good. So what we did was, in order to get precise information from these tools and give them precise information, we built 3 ontologies, which are based on ice cream. Right, so the first thing is when you, sorry, something's not linked right. So quite often, the sort of things what you're used to saying is, yes, it's a theorem, or no, it's not a theorem, or these axioms are contradictory, they're unsatisfiable, or these formulae are satisfiable. These are the standard sorts of results that you get from a reasoning tool. But we also want it to be more precise. There's a difference for something being a theorem because it's that, or because the axioms are contradictory. Remember my early picture? If your axioms are contradictory, you get free beer. So, I mean, theorem provers, some of them will say, hey, I proved this by finding a contradiction in your axioms, and that's useful information. So we can get very precise information out of this ontology. So when you run a tool, it will tell you one of these very precise categorizations of what's gone wrong. But also, when things go wrong on the internet, this is all coming live, you want to know why things have failed. Segfault core dump is not a good answer, right? Or no, or I give up. But we have a very precise ontology for failure. Why has the tool failed? And that gives the user some feedback on how they can change their axioms or reformulate the problem like that. And that's a very useful thing. And if you know Alan Bundy from Edinburgh University, you might read his good paper called The Productive Use of Failure, which is something that inspired us here. So we have things like here, as you see, is that there was timeout and you ran out of CPU time when you were running. Or, for example, there was a syntax error in the input, or what's another example here? This problem is inappropriate for me. My tool doesn't know how to deal with this particular language segment, particular logic. So we can get precise information about failure as well now, which is nice. And finally, what we also have is another ontology I need to fix that picture, which is to say, what sort of data? Did you get a proof out? Well, maybe there's more than proofs, aren't there? Because you can have a proof, but of course, the type of proof, most of what we are finding are refutations, because we're doing proof by refutation. On the other hand, if you have using a Tableau type method, you might have something else like that. Types of models, finite models, infinite models. Again, so you know what the data is, and then you can use it. As you're going to see now, when I went on to the next phase, I used all of that to build the solution library. So I wrote to all my friends and said, send me your theorem provers. And they did, and I compiled them up. And I currently have a cluster. Does anybody use star exec here? No star exec, all right. So these are two, one in Iowa and one in Miami, which are designed for running big experiments where you've got lots of problems and lots of tools, and you want to sort of run the matrix, and you have a whole big thing there. It's, all right, well, it is. And so I did that, and I ran all the theorem provers on all 26,000 problems. I do this about every 3 months and see how things are progressing, because I can even see progress in the state of the art as problems get solved by more systems. So their rating starts at 1 and slowly slips off down to a low number, and you see that's progress in the state of the art. It's kind of interesting to do. That coming out in AI index again. And of course, you say, if it says timeout, the obvious answer is, well, just give it more time. This is a semi-decidable logic, just double the amount of time. Who cares? It's only hardware. Run it on Amazon. Just give them your credit card. They'll give you more CPU time, as much as you can afford. But it turns out that that's fruitless, because this is a little bit old data I can see from these, but these are first order form problems that are solved in the solution, and I said, how much time did it take to solve them, and sorted them by order. So this guy over here is Vampire. He's the powerhouse. He solved something like 10,000 problems in some of these weaker systems. But they all have this curve that goes like that, which shows that if you, after 150 seconds, if you double it to 300, you don't really solve many more. The line doesn't get much further to the right. So if you, in practical terms, if we're using these tools, you don't need to really give it more than about 2 minutes. After that, the wheels start to fall off. And this is, I've done this picture so many times, and it's totally, there are variations on it, and some of them have a slightly slower curve, but all of them have a point where things go wrong. And I call it the Peter Principle point. I don't know if any of you have read books on management theory. The Peter Principle is this theory, and it occurs in university administrations and government organizations a lot. People come in, they get a job, and they perform well. You're doing your job well, so you get promoted. You perform well, and you get promoted, and you perform well, and you get promoted. And you get to the point where you can't do your job well anymore. You've just got past your level of competence. All right, then you leave people, they're doing their job badly for the rest of their lives. And that's the Peter Principle point. Now, in active business, the technique is when someone's promoted to their level of incompetence, you keep them at that salary, but demote them back to where they're competent and do the job well, and the business thrives. But that's what's happening here. These tools have a Peter Principle point where they get to their level of incompetence. All right, so that's the story. So we did this big matrix, and we have a language for writing proofs and a language for writing the models, the data structures that show consistency. And it's the same language as for writing the problem. There's only one language. This whole thing is consistent. So if we look at a example, this is the proof of the Aunt Agatha problem. I can see from a fairly old theorem prover. The language looks strangely familiar, doesn't it? It's exactly the same language. What does that mean? If you're a Unix, Linux user, you can run one tool, take the standard output, pipe it into the next tool, and pipe it into the next tool to build pipelines, reasoning pipelines. And so if we take an example, let me find one that's not too boring. So this piece is somewhere in the middle of the proof. It says this is a representation. The killer hates Agatha, done by some inference rule called SPM, some form of superposition, I don't care. And it came from number 33 and number 20. So you can go and find number 33. That's just the names over here. So we've got all these proofs, and this is useful stuff to have. We have a library of 84 provers times 26,000 problems. Well, not all, about half of it's populated, because sometimes they're not suitable. And then you can go and look and say, how did that guy manage to prove that? That's fantastic. And then you cheat.
So what is the proof system for first order logic?
It's classical first order logic proof by refutation. In what sort of sense do you mean?
You have specific
so
rule of inference or
well, you should
classic?
you should attend after the break. Or something I can talk. Yeah, I mean, there's not. I mean, you can have modus ponens type rules if you want. They all have lots of different inference rules. All of them are sound. Almost all the rules are sound, but the main thing is that the rules are satisfiability preserving. So, conversion from first order logic to clause normal form is not an inference, but it's satisfiability preserving. That's actually for after lunch. I can explain how all of that works. People interested in the background. So we have this language, and again, you can get it from your homepage /TSTP. So we did that, and that was fun. And then I'm just watching. What is the time deal exactly? I need to just watch. So I've got lots.
So we are 9:40 now.
Yeah, but I've got 20 more minutes.
Yeah,
Schedule this
For now.
from 9 to 10. Yeah.
Okay, all right. Okay, so I just want to say, so one of the things we do is I've seen we do problem ratings. We have a nice algorithm for rating problems, and I'll quickly explain it to you because it can be used for anything. If you're evaluating software, different types of software over a data set, and you want to know how hard are the problems and how good are the solving software, this is the technique. If you think of this box as being my 26,000 problems, there's some little colorful dots, and those are the little dots where people said, here's a problem, put it in your problem set because that'll mess up him. Right, so we can't, that's kind of next. So we get rid of them. And then we split it up, the problems into homogeneous classes that aren't Agatha problem I showed you was first order, really first order, it can't be reduced to propositional. It had some equality, I can't remember the other property I had about it. So we grab one of these little boxes and deal with one of these little boxes independently. So now I've got here 4 problems and I've still got my 86 provers. All right, so then here's an example. In this, I've got 1, 2, 3, 4, 5 different theorem proving software. It's any software, and the black dots represent problems. And you can apply this to whatever you like, this idea. Well, you can see this orange guy is definitely worse than this red guy. He solves a strict subset. Huh? Similarly, purple is strictly worse than green. So what we can do, let's just get rid of those guys. That's stuff that's not worth considering. And so if you've got what's left, this is everything that can be solved, the union. Notice the long skinny guy is somewhat different to the others. It's okay to be different. It's all right to be different, Then we very simply, for the black dots, we say what fraction of the remaining system solve it. Nobody solved the yellow area. Everybody solved the brown area. And that gives you a difficulty rating on the problem relative to the state of the art of your software. And you can do this with any type of software. And people say, oh, okay, but that's kind of useful because when you're writing your theorem prover for your first time, you want some easy problems to test on, you go and look for those, the real easy ones. And when you think you're a super genius, you go and get some of these ones in the yellow area and say, let me try and solve these. And say, I can solve one of those, and you write me an email. I can solve a one problem. But then people are more interested in knowing who's got the best system. Software competitions are just rife in the computer science community, and I run one of them. So what do we do here? Next button. So what we do is throw away the problems that nobody can solve because they don't differentiate. Right? Throw away the problems that everybody can solve because everyone can solve them. They don't give you any difference between the systems. And then you look at, for all of the systems, what fraction of the remaining problems they can solve. And that tells you how powerful the system is. So you can see this little guy is powerful 0.6%. He's an 11%er, and the big green guy is a 55% powerful system. And that's useful. Yes.
Isn't it a problem how you encode your problems? So, I mean, the encoding clearly will have an impact on, I mean, it may very well solve, a system may solve a problem, but your encoding is not appropriate for the tool. So, I mean, there is a correspondence here.
It is with respect to my set of problems. What I've observed is that, so for each problem, we have often have many different encodings that people say, this is how I would encode it.
Yeah.
And we try all the we use all the encodings.
Also, you have a set of encodings.
Yeah, for many problems, we have many different encodings as well. So of those 26,000, I think there's like 18,000 unique problems in the abstract sense. And some of them have been encoded in multiple different ways.
So in theory, if a tool says, oh, drive, well, I mean, if they say not fair, then they can provide their.
Yeah, they just send me an email, say, look, here's how I would do it.
Yeah.
And I put it in. And then, but you're right, there's some fuzziness at the edges of this rating scheme, but it does reflect the current reality because I have all of the current tools and I have biggest test set. You know, with any testing of software over test set, it's always fuzzy because what does the test set mean? You know, you choose your own test set and things are groovy for you. But because I'm not biased towards any solver in any piece of software, I think this does give an accurate reflection of what's working well. But you're right, there's some give and take at the edges. You're quite right. All right, so just quickly about some tools. So as I've said, in Miami, I have this big cluster that I do my big experiments. I also have 3 computers paid for by the American taxpayer. Oh, thank you. Which provide services, and they're free, and you can use it. It's all online. Does anybody use Isabel? Isabel Sledgehammer, a little bit vaguely. So you know, Sledgehammer, Isabel's an interactive theorem prover used for developing theories and doing analysis of protocols and stuff. They need automatic provers underneath. So they call my provers in Miami about once a second, get a blip. The advantage of using my tools rather than installing on your own laptop is I know the prover developers and I have the latest, hottest stuff all the time. So I have the most powerful things available and it's free. And you don't have to install it. You can programmatically call it in Perl or new Perl in Python, C or Java, whatever you like. You just as long as you've got internet, call Miami and it comes back. So let's see this all happening. So here's that problem about Aunt Agatha. All right. Well, rather than taking the whole problem, I could just go and solve it, but let me show you it. I'm going to copy out the formulae, the non-comment stuff. And then one of the tools that you use to solve a problem is this one here, the system on TPTP. Click there. There we go. So you can choose a problem from my library of problems, or if you've written your own, you just paste it in here and then choose your favorite theorem prover. And you notice I've got lots of them. All right. So I'm going to use this one because it's a nice robust one from Stefan Schultz in Stuttgart. And I click go. And something happens, goes to Miami. People stop doing the salsa, look at the problem, come back, and still churning away there. I think this is network lag. There we go. So it ran it, and it said yes. And there's that status from that success ontology about the ice creams. It says, yes, this is a theorem. And this is from the data form. It says, what I'm going to give you as output is a proof by refutation in clause normal form. And here's the proof. And you look at that proof and you think, what shit? You can't understand that. So reverse engineering the proof up to something that's human readable and usable is part of the game. So what we can do is turn on the proof viewer. And this is, again, going to take a bit of time. JavaScript, lots of JavaScript. Written by undergraduates, so it's not very compact. So, coming down. Positive. All right, here it goes. Yep. And then now the JavaScript. Yep, here it goes. And there you see the proof. All right. And so you can see this is a proof by refutation. There's the conjecture. We see it over here. The little house, trying to Agatha build Agatha. It's a proof by refutation. Negate it, turn the house upside down. There's the axioms, the little triangles. Here's a whole lot of inferencing, like what Sash was asking. This is mostly resolution, superposition, inferencing in this prover. All right, And at the bottom, the little box, as you can see, says false. We've found the proof by refutation. All right. And then you think, but this is a small one. Right. And when you've got 10,000 nodes, it's kind of looking cool. So this you could kind of analyze by hand. But we've got this nice tool. The interesting, this tool stop happening in Miami. And what it does is it looks how interesting each step is in the proof. What does interesting mean? I can give you the paper. This is work I did with one of my students. What it means, big circles are interesting things and little circles are boring things. That's kind of nice because now you can go, get rid of the boring things, boring stuff. Well, let's leave 4, okay? And we'll just remove the back ones. Sorry, that sounded very racist. So this is what it thinks is interesting. So what's number 48 say? Scroll this down again. It says the butler does not hates butler. The butler does not hate himself. Oh, interesting. That's useful. Number 46. That one says the butler hates the killer. That's the scoring function for people who know about that. And here we go. That bottom one, the killer is Agatha. And there we go. So what have you got here in a mathematical sense? What do you call interesting sub-results in a mathematical proof? There's a word, begins with an L. Last letter is A. Middle letters are M, M, and E, but not in that order. No, it's a lemma, right? Yeah. So this is how you find lemmas. So that project I mentioned in Albuquerque with real mathematicians, they have proofs like this, but with 10,000 nodes. So they run this, and then they get a proof summary out of it like that. And then they can say, oh, that's an interesting step in the proof. And it helps them develop their theories of reading, mapping beyond my map level. Of course, if none of that made you happy and you have children, there's another use for this. You take your 3-year-old child and say, oh, look at the pretty lights, look at the pretty lights. So it has other uses as well. Where were we up to? Okay, so we've got a lot of these tools available, free to use. And my plan for after the break and however long people want to is to show you how to use those tools. So if you ever need a reasoning tool, you can get out your laptop, you don't have to install anything. All you got to do is learn my very simple human-friendly syntax and click, 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 and you can start doing proving straight away. And whatever you want to formalize, be it software, be it your life or love life, anything like that. You can prove that your love life will be inconsistent, for example.
You get free beer forever.
Okay. Watching the time. So lots of applications that we've done. This was one of the fun ones. I worked for NASA Ames with some people. And what they were doing with this is they were, rather than write software, they had software that generated software in C++. So they'd specify the problem and hand it over to a software generation system, which would produce code, and that would run. We were doing stuff to the space telescopes. It turns out you have to have very good software because once you send a space telescope up, you can't reach up and do a Microsoft Control-Alt-Del, they're too high. So what we did, they wrote safety policies of what they expected from the software, which got fed into this synthesis system, generating C++. And we would get C++ code with verification condition. The verification condition generator that produced logic problems. We'd run these logic problems through a theorem prover, like one of the ones E that I just showed you. And it would come out. And initially, we didn't have the proof checker. The proofs just went straight out over there. And we had proved properties of the software that had been automatically written by this synthesis system. And then you give that software to the FAA, because they controlled space in those days, and they'd say, no, this is not acceptable. People are much more reliable than computers at generating software. We can't accept this computer-generated software. And first you look at them, oh my God, people, unreliable if anything goes. Anyway, so what we did is we took out these proofs and put them through a proof checker. I have proof checkers available online. If you don't trust your tool, you hand it to a proof checker. And rather than you look at all that squeege of output I show you and you analyze that line by line. And we did that and gave a certificate. And then the FAA were happy. And it was funny. Now we knew they were happy because they came with a little van with FAA logo on this side. And we had boxes of these printouts of proofs. And so we'd put them in the back of their van and they'd go away and come back and say, yeah, we understand, yeah, everything's okay. So it was proof by weight. They accepted if it was heavy enough paper. We didn't understand it, but eventually the software was all acceptable to those people. So lots of things we've been playing around with. This is something I run every year, which is kind of exciting. I run a competition. This is the CADE ATP system competition for all of those serum proving tools. So about 20 of them enter every year. And we have a competition. I choose some problems randomly based on a random seed provided by other people. Everybody has to read my syntax. And so this we conceived back in '94 because we had the TPTP, we had all the problems by then. And so now it's an annual event, and we actually in July this year, we'll be at the 30th version of it, 30th edition of the proof. What do we do? So we test them and they get a time limit. The time limit is past the Peter principle point. I always give about 3 minutes. So we know that they're not going to solve much more if we doubled it like that. So it's safe. And we just look, how many problems can you solve? Right? And we test them that they're not just printing yes. We do some look for soundness testing. And lots of results. But so what is the advantage of a competition? Everybody, I don't know if anyone do programming competitions, or you're an athlete and you do running, or you play some sport, or you play cards, and this competition is fun, right? It motivates people. It's insane how many hours, how many days a graduate student will work without sleep to get a $10 trophy, plastic trophy. All right. You give them a salary for 6 months and I mean, I don't understand it, but if you're an athlete, you train like shit for competitions, don't you? But if you're not going for a competition, you say, oh, I'll just skip the run today. You know? So what do? We saw some problems is that by running the competition every year, people didn't have enough time to really do lots of development. So I'm moving to a 2-year cycle starting again. And one thing we saw is people were taking my set of problems, which we're choosing from, and tuning their system with special parameters. They were hyperparameters for being well fit. So I fixed them. Every year I put up a whole lot of new problems and I choose those first. So they get problems they've never seen. It's like when you go for a run, you run on a different track or something. So it's just got to be good. Lots of implementation work, which is true. And implementation often lands on the hands of postdocs and grad students. And truly, we were in Munich one day, and Andrei Voronkov and Reinhold Letts pretty much got into a fight because they were neck and neck. The results come out live in real time. We really had to separate them. You're cheating there. No, I have a special team. You liar. All right, but it does evaluate the systems. We know what's good. It tests the theory. Theory is only worth the papers that are printed on, right? If you've got a theory, implement it. How well does it work on current hardware, current constraints, current data availability? Implementation, as I've said, it rewards the people who do it. They stand there with their $10 plastic trophy and say, look at me. Yay. But it does stimulate research for sure. People like to work hard and compete. And your system has to be autonomous and it has to work. Single core dump doesn't work. You've got to have robust software. And we expect that in general from computer science. We want software that's high quality, always works, or at least if it can't solve a problem, it fails gracefully. All right, I mentioned this fighting. And then sort of, it does. People will watch a competition. We have it up on a screen like this at the conference. People sit there with their coffee and cake and they're hyped up on caffeine. And lots of competitions have come out. You can enter my competition. And why would you? Because we have fantastic t-shirts. This is a big, maybe let me just go back. I want to make a point here. When Christian and I sat together in Nancy in 1994, we decided from the get-go that our competition would only be 50% about who's the best, but also 50% about stimulating research, making people talk to each other, having fun. So it means that people who are new in the community would meet the senior people, find out how they do it. People would exchange ideas across the dinner table. We have a dinner and all sorts. And we have t-shirts, and the t-shirts are just, come on, internet. And I think I've won too many bets about inconsistency sometimes. I like this one. This is when the conference was in France. So I had the body actually cutting off the container. Agility. I don't know if you remember. That was drinking in Brazil. This was the year of COVID when the conference got cancelled, but I don't know if you had it in America, toilet paper was a shortage.
Yeah.
This was the toilet paper t-shirt. And this is last year. So how do you enter it and get a t-shirt? You can write a theorem prover that's eligible by in one line of Python. Print F or print I give up. It never gives the wrong answer. If you want 0, if you enter the competition, you get a t-shirt, you come to dinner, you meet people, it's wild fun. And we have gambling as well, by the way, like all gambling. And so you could win money on the gambling as well. So I encourage you to enter. Okay. So let me kind of finish up now. Of course, this is ongoing work. And we're always working on new things. We're working very hard on the data structures that explain why a theorem cannot be proved or why a set of axioms is consistent. We've got a new standard for that, and that will come out. We're also doing verification of proof using lambda pi deducti for people who enter type theory with the groups in France. Different types of proof, connection calculi, Tableau. I mentioned the star exec cluster. We now have almost finished implementing it. And if my postdoc hasn't finished it by the time I get to Miami, he won't be my postdoc anymore. It's all in Amazon and Kubernetes. So if you want to run big experiments, we have a whole software framework coming out that will be free. We're interested in more expressive logics. All right. So we're interested in things like multi-value truth, like RM3, RME or FDE, RM3, LP, and all of those things. And we have tools for that come available. That hasn't developed so much. Lots of stuff on modal working already and answer extraction. So the end, why does this all work? And then I'll finish. So firstly, one of the reasons it works is a lot of people have helped me. But one of the things happened, everybody like the octopus puts in, and I sit in the middle of this and I don't actually do anything. I just like the conductor of an orchestra, but make sure everything is homogeneous. The whole framework fits together very tightly, which gives you in any software system or any organization, a train system. I love the train system here, by the way, it's fantastic. I came from the airport on the T8. It's sort of a homogeneous, everything fits together very well. The languages, one language used for everything, one way of doing things for everything. And I was mentioning this, we were just talking about it. Richard O'Keefe is a professor in New Zealand, I think he might have retired now, who wrote a beautiful book called The Craft of Prologue, like this. And at the front of a book, people often write, thank you to my children for being, being nice to me while I wrote the book, and thank you to my parents who loved me while I didn't study. And he just wrote at the front of his book, elegance is not optional. And this is about Prologue programming. Writing elegant software is critical in life. It's not just Prologue. Inelegant hacks eventually die from bit rot. So I have my own. I will write a book one day. Compliance is not optional. But then I started seeing a strange effect over the years. I said I started this in early 90s, and that's what I looked like back then. And that's Tim Gray, the XML guy. And this was Christian Suttner, my colleague from Munich, who started it. He went to industry. Look what happened. Larry Paulson used my stuff. Bill McCune, unfortunately now dead, from Argonne Labs, had his own language. Bernd Fischer from NASA used my stuff. Christoph Beidenbach from Max Planck Institute, DFG syntax. All right. Joseph Urban from Prague, Volker Dieke, total theoretician. Alan van Gelder helped me write parsers. Alan Bundy from Edinburgh had his own language. Kun Clarkson, nothing. This guy, I was at a conference in Copenhagen. I went up to him, I said, I bet you don't use the TPTP. And he said, I don't. How did you know? So then I thought about Michael Klim, this famous Australian swimmer from some years ago. And unfortunately, he got ill, right? It's the story, but absolutely amazing character. I mean, this guy could swim. And I thought, imagine if he used the TPTP. He would look good. So, and that's sort of the end of the story. Well, now I can take questions now. We'll stop for a break, and I'll be here all day. Cheers now. Yeah.
Let's thank Geoff. So we have a 15-minute break. After this, until midday. After that, until midday, we have a practicum where, you pull out your laptop and Geoff will run through actually getting us to use some of the tools. And then we'll have lunch. We'll probably go to Broadway or something like this, 12 to 1:30. And depending on interest, there'll also be an afternoon session as in the advert. So feel free to come and to attend whichever parts are most interesting to you. All right.
Yeah, after the break, it's just real practical. It won't be any high logic, no Greek letters or anything like that. Just here's what's available, here are the tools, here's how you should use them in order to do it in a proper way, using my stuff free. All you need is a laptop with a browser. Just remember to set your homepage.
Thank you. In 15.